Hello everyone, how are you? Very good afternoon to all of you and very good evening to all of you. So am I audible and visible? Give me your answers in the poll. Students, am I audible and visible to all of you? JNV Morbi students, Drex and Episaka, Manish, Vaishnavi, Roshan, Sri Lakshmi, Trisha, Vaibhavi, Bhaktoy. Can you all able to see me? Can you all able to hear my voice? Yes. Am I not visible and audible? Yes. Okay. Okay, thank you so much students for your responses. So now we'll go ahead with the session. Sorry for being little late. Okay, I had to complete my 12th standard class and come back here. So I took a little bit time over there. Sorry for it. Yeah. So now we will go ahead with the equilibrium lesson. Okay. So what topic we have discussed in the previous class of this equilibrium? Can anyone tell me the topic? Manish, can you able to hear my voice now? Am I audible? Is it okay now? Okay, fine. So guys, tell me, what is the name of the topic we have covered or discussed in the previous session? Do you have your notebook with you? If you have your notebook with you, you might have given me the answers by now, right? So what was the topic we have discussed in the previous session? Oh my God. Okay, let me recall it, okay? So the first topic is about the equilibrium constant, the types of equilibrium constant, the properties of equilibrium constant, those things we have discussed, right? There were two types. One is with molar concentration and the other one is with the partial pressure, so Kc and Kp. And also we have discussed the relationship between Kc and Kp. Okay, Kp is equal to Kc into RT power delta Ng, okay, which is a very important relation. And we have studied 5 properties of equilibrium constant. Among those 5 properties, 3 of them were very important, I told you, right? So what is the first among that? If I reverse the equation, then the new equilibrium constant will be the reciprocal. And if the equation is multiplied by some number n, then the new equilibrium constant is equal to k power n. And if 2 equations are added, then the new equilibrium constant will be the multiplication of those. Okay, and later on we have discussed about Q also. I have discussed about the reaction quotient. If they are equal, they are in equilibrium. If K is greater, the equilibrium will move towards forward direction. And if Q is greater than K, then it will move towards backward direction. Okay, and finally, we have discussed the applications of equilibrium constant. There were 3 applications, and the last application is very important, which is actually the relationship between delta G naught and KEQ. The formula which we have already studied in thermodynamics lesson as well as in the application. Okay. So this is all we have covered in the previous session. Now coming to the new topic for today, which is called as Leach Atlas principle. So this principle says that a change in any of the factors that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of change. So the meaning is, let me take a reaction. Okay, I'm taking a reaction where the reactant are getting converted to the product. Okay. So if I try to disturb this equilibrium by increasing the concentration of the reactant, or by decreasing the concentration of product, or by increasing the pressure, or by temperature, if I try to disturb this system, okay, system means the reaction, the reaction will try to keep themselves in equilibrium by nullifying the effect which I have made on the reaction. Okay, it will try to manage itself. If I increase the concentration of reactant, what it will do? The reaction will move towards forward direction. And at one point, what will happen? Both the reactant and product will be in same amount and they will be in equilibrium. Okay, if I increase the concentration of the product, then the reaction will move towards left side, towards backward direction, and they will have the same value at one point. Okay, so if I try to disturb the equilibrium, if I try to give some stress to the equilibrium reaction, it will try to nullify the effect which has been put on the reaction by counteracting the effect. Okay, so this disturbance can be caused with the 5 factors. First is, I can disturb the equilibrium by changing the concentration. Secondly, I can disturb this by changing the pressure. Thirdly, I can disturb this by changing the volume. Fourth is changing the temperature. And fifth is by the addition of inert gas. Okay, you all know what is inert gas, right? The non-reactive gases are called as inert gas, mostly noble gases. So I can disturb the equilibrium by these following 5 factors. By changing the concentration, pressure, volume, temperature, and by the addition of inert gas. Okay, so let us discuss one by one. And let us see how it is going to change the equilibrium, how it is going to affect the equilibrium. Got it? So let me go from the first. Let me start with the changing the concentration of reactants and products. So to understand this, I will take one reaction for you where Fe3 plus is reacted with SCN minus and it gives FeCN 2 plus. This is a coordination complex. So initially the Fe3 plus ion is yellow in color and in the product it is deep red in color. Now again the reaction can go back to the backward direction. They are in equilibrium. Okay. So if I write the equilibrium constant for the forward reaction, then it will be Kc is equal to the product concentration divided by the reactants concentration. Okay. So this is the Kc for this reaction. So who are the reactants? Fe3 plus and SCN minus are the reactants. Okay. And the deep red color complex is the product. So keep this in your mind now and see this tabular column. So I'm going to give you the tabular column, okay, in which the change in concentration is taken in the first column and the direction of equilibrium shift is taken in the second column. To that reaction, if more amounts of reactant is added, then the reaction or the equilibrium will shift towards forward direction. Okay, so I have A and B and it is giving C. This is the reaction. They are in equilibrium, right? Now, if I increase the concentration of this reactant, suppose initially I might have had concentration as 5 mole per liter here and here also 5 mole per liter. And if I increase the concentration to 7 mole, what will happen? I have to keep the reactant and product in the same amount. So what this will do, the reactant, some of the reactant will be converted to the product. So the equilibrium will move towards, the reaction will shift towards forward direction by keeping 6 in both the case. Okay, 6 in both the case. And if they are in equal amount, then we can say they are in equilibrium with each other. Okay. So if I add more amount of reactants, then the equilibrium will shift towards forward direction. Got it? If I remove the reactant, what will happen? The removal of reactants. If I remove the sum of the reactant, the equilibrium will shift towards backward direction. So the product, some of the product will come back to the reactant side and they will try to keep themselves in the equilibrium. Okay. In the same way, for addition of product, it will move towards backward direction. The removal of product will lead to the shift in forward direction. Got it? This is actually easy. If you understand, it will be easy. Okay, you don't have to worry. If you are taking, you can take some time also to understand this concept. Okay, if you're getting any doubt, you can ask me. You can take some time also, but try to take a snap of this page and keep it with you, or write down the things in the notebook which you are having with you. Please go through it, revise once again, you will understand. Got it? If you do not understand this now, no problem. You can take some time and go through this, okay, for your better understanding. So shall I go ahead with one question to understand this concept better? Shall we go ahead with one question, students? Are you all ready? Yes or no? Yeah. Very good, Roshan. So here is the question. Describe the effect. Yeah. Yes, Manish. Describe the effect of the four cases for the given reaction. So can anyone try? So we have two reactants, H2 and CO, and it is giving methanol as the product. What happens if I add more amount of H2 to this reaction? Will the addition of more amount of H2 lead to the or shift the equilibrium towards forward direction or backward direction? If I add more H2O, will it lead to the formation of product? Will it go towards forward direction or it will go towards backward direction? Very good. Because addition of reactant will shift the equilibrium towards forward direction. Very good. So in the first case, it shifts towards, the equilibrium will shift towards forward direction. What about the second case? Addition of methanol. Very good. Backward. Because it is a product, right? So it will shift towards backward direction. What about the removal of CO? If I remove the reactant, some of the product will be converted to the reactant to have it in the equal amount. So, very good. The removal of CO will shift the equilibrium towards backward direction. What about the removal of methanol? What about the removal of methanol? Very good. So, if some amount of the product is getting removed, some of the reactants will be converted to product, and it means that the equilibrium is shifted towards forward direction, right? So in the last case, equilibrium is shifted towards forward. So forward, backward, backward, and forward. So this is the answer for this question. Can you all able to understand now? Shall I go for the second factor that affects the equilibrium? So what is the second factor? First is changing in pressure. Yeah, sorry, first is change in concentration. The second is changing the pressure. So let me take one more reaction. where the brown color NO2 gas is getting converted to a colorless N2O4 gas. And you can see that the delta H associated with this reaction is minus 57.2 kilojoule per. If the delta H is minus, then it means the reaction is exothermic, right? Exothermic heat energy is released from the reaction. And brown color is getting converted to colorless gas. For this case means there is the NO2 gas present in the system and I have applied some pressure and the NO2 has been converted to N2O4. Okay. So now for this case, for changing the pressure, you see here, if the number of moles, the change in the number of moles is greater than 0, that is if the number of moles of the product is greater than the number of moles, then on increasing the pressure, the reaction will shift towards backward direction. Okay, again I'm telling you, don't worry about the direction and the condition. Just write this in your notebook. Take time. You have to take some time to understand this. Then only you'll get clear idea about this. Okay. So just by seeing the slide now, there will be some confusion arising for you. So don't worry about that. Okay. Just think and do it. Take your time. And in the second case, for the same condition means the number of moles of product is again greater than the number of mole of the reactant. If I decrease the pressure, the equilibrium will move towards forward direction. Okay. So in the first two cases, number of moles of product is greater. In the third case, number of moles of the reactant is greater. Okay. If the number of moles of the reactant is greater and if I increase the pressure of the system, equilibrium will shift towards forward direction. And for the same case, if I decrease the pressure, it will move towards backward direction. If number of moles of product and number of moles of reactants are equal, then what will happen? Whether you increase the pressure or decrease the pressure, there won't be any shift because the number of moles is same for both the reactants and products, right? So there will be no effect. The equilibrium will neither shift towards forward direction nor shift towards the backward direction. Got it? So please take a screenshot or take a snap of it or write down in your notebook. Study this later. It will be very helpful for you to solve some of the conceptual based questions coming from this topic. Okay, this is all about the changing the pressure factor. Shall I go ahead with the third factor? Changing the volume. Students, shall I go ahead with the third topic? Which is changing the volume. Have you all taken this down in your notebook? Okay. Changing the volume. At constant temperature, volume is inversely proportional to the pressure. Right? If I increase the pressure, volume will decrease. I have a system and I have some gas molecules. This is the initial volume V1. Now, if I apply some pressure on this, what will happen? The gas molecules will come closer to each other. Okay. And this is V2. So what is happening? If the pressure is more, the volume is less. If the pressure is more, volume is less. Means pressure and volume at constant temperature, they are inversely proportional to each other. Okay. Now, if I change the volume of an equilibrium reaction, how does it going to affect the equilibrium? So, for the same case, for the same number of moles of product, if it is greater than number of moles of the reactant, increasing the volume will shift towards forward direction and decreasing the volume will shift towards backward direction. Okay, for the first two cases. If the reactant number of mole is greater, Suppose let me take this as reactant and this as product. They are in equilibrium. Okay. If the reactant number of moles is greater, then increasing the volume will shift towards backward direction and decreasing the volume will shift the equilibrium towards the forward direction. And if they are equal, there is no shift. This is the same as that of the previous case. Okay. It's the same as that of the previous case. Only thing is you need to change this volume instead of pressure. Got it? Shall we solve one question from this concept? Shall we solve one question from this concept, students? Say yes or no. If you need some time to write, you can tell me that you need some time. Please don't stay silent. Okay. Okay, Manish and Trisha, let's go ahead with the question. Okay, Vaibhavi. So here is the question. Does the number of moles of reaction products increase, decrease, or remain same when each of the following equilibria is subjected to decrease in pressure by increasing the volume? Can you all able to understand the question? You have to tell me whether the number of moles of the reaction is getting increased or it is getting decreased or it is remaining same. When each of the following, when each of these ABC, when each of the following is subjected to decrease in pressure by increasing the volume. Decrease in pressure and increasing the volume, both are same only. Okay, just take any one to avoid the confusion. When the reactions are subjected to decrease in pressure, what will happen? Tell me. Take PCl5. Take PCl5. Okay. So in case of PCl5 reaction, we are getting PCl3 and Cl2. Okay. If the pressure of the system is decreased, then the equilibrium will shift towards the side where more number of gaseous moles are there. Where more number of gaseous moles. Roshan, you are really doing a great job, you know. So if the pressure of the system decreases, then the equilibrium will move towards the side where more number of gaseous moles are there. Where more number of moles are there. Okay. So what is here given here? In PCl5, we have only 1 mole. And here in the product side, we have 1 PCl3 and 1 Cl2. The product, we have 2 moles. In the reactant, we have only 1 mole. So the equilibrium will shift towards the direction in which more number of moles are present. Okay. So what will happen? In the first reaction, it will move. The reaction will move towards the forward direction. Equilibrium will move towards the forward direction. Got it? What about the second case? What about the second reaction? Will it move towards forward direction or backward direction? Gaseous moles is very important. Okay, you should not have a solid or liquid. You should have gas. More number of gaseous molecules should be there, and to that side, the equilibrium will shift. Okay, very good. It is backward. Because in the reactant, we have 1 solid and 1 gas. We won't take the part of the solid. And also in the product, I have only 1 solid, calcium carbonate. So, in the reactant, we have 1 gaseous molecule, 1 mole of carbon dioxide is present. In the product side, there is no gaseous molecule present. So, the equilibrium will shift towards the direction in which more number of gaseous molecules are present. Okay. So 0 is greater than 1 is greater than 0. So the equilibrium will move towards backward direction. Got it? For the second reaction, it will move towards backward direction. And for the third case, what is the answer? To which direction it will move? Very good, Trisha, Roshan. In the third case, there is no shift because we are not going to consider this solid part and there are two gaseous molecules. Each of them are in the same number of moles, 4 moles each. So the number of moles of product and the number of moles of gaseous reactant are equal. Yes, Rakshita. Rakshita, where were you for the past few days? I could not see you. Huh? Today only I have seen you, I think, after a long period of. Okay, anyways. So in case of the third reaction, NP and NR, both of them are equal. So there is no shift and the concentration remains same. Got it? So this is all about the third factor. So you have to find out. Just keep in your mind, equilibrium will shift towards the direction where the number of moles is more. Okay, so that's all. Now coming to the fourth factor, which is called as changing the temperature. Let me take the same reaction which I have taken for the second factor. And here, if I change the temperature, and I already told you that this is the exothermic reaction since it is given in minus. Okay, the negative delta H containing reactions are exothermic in nature, means the heat energy is released. Heat energy is released. Okay, now you see, if the type of the reaction is endothermic, that is if the delta H is greater than 0 or if it is positive, then if you increase the temperature, equilibrium will shift towards forward direction. Okay, it is endothermic. Energy will be absorbed by the system. And if you still increase, if you still give heat by increasing the temperature to the reactant, it will keep on absorbing. So A is giving B. This is the reaction. They are in equilibrium. If you are keeping on increasing the heat, the reactant will keep on absorbing the heat in one side. So if they want to keep themselves in the equilibrium, what does A has to do? A has to shift the equilibrium towards the forward direction. Then only some amount of heat which is given to this A will be moved towards B and they will have the same amount of heat. Okay, so increasing the temperature for endothermic reaction will shift the equilibrium towards right side and the decreasing the temperature will move towards left side. Decreasing the temperature means the temperature of A is getting reduced. So in that case, B will help A. B will give some of its heat to A. So it means backward reaction will take place. Okay, B will give the heat no to A. So backward reaction will take place. And for exothermic reaction, exo means heat energy is released. Heat energy is getting released. It is getting released from the reactant side. So even though if I increase the temperature, the heat energy will one side go on releasing. And in that case, backward reaction is favorable. And for decrease in temperature, forward reaction is favorable. Got it? So please take the note of the tabular column again. All of you please take a note of this tabular column for changing the temperature. So this is the fourth factor which affects the reaction, which affects the equilibrium according to Le Chatelier's principle. Okay. Shall we go for the fifth factor, which is addition of inert gas? Have you all completed? Yes. Fifth is the addition of inert gas. So this addition of inert gas can be done with the two things. One is at constant volume, I can add some inert gas. And the other one at constant pressure, I can add the inert gas. So first, let me go for constant volume condition. So let me take a system in which I have some gas molecules. Okay. And this is the system is getting the constant volume is remaining constant, and the violet color balls are inert gas. Blue is the product and green is the reactant. Okay. So the reactant and product will be in the same amount and the volume is also same, but inert gas is added. So in the first container, all of you please look carefully. We don't have any purple color or violet colored balls, molecules. But here in the second container, I have the purple colored balls, right? Can you all able to see? So these are the purple color balls, which are nothing but the inert gas molecules. So now you tell me, will there be any change in the concentration or the change in the partial pressure of reactants and products by the addition of inert gas? Will there be any change? Inert means it is non-reactive, right? Inert, what is the meaning of inertness? Non-reactive. So in addition of inert gas will not react with the reactant or the product. Okay, so there is no change in the molar concentration or partial pressure of the reactants and products. Okay. If there is no change in the concentration or pressure or other things, equilibrium remains undisturbed. Equilibrium remains undisturbed. Okay. So for constant volume condition, whether you are adding the inert gas or not, nothing is going to change. The equilibrium remains undisturbed. Okay. But when you come to the constant pressure condition, at constant pressure, if I add the inert gas, you see here. So this is the first container where I don't have the inert gas. Now, in the second container, you see I have the inert gas. At constant pressure, what is happening? The inert gas molecule, the concentration or the partial pressure is changing. Okay. So why it is changing? Because the volume is increased. Volume is increased. Pressure is constant, but the volume is increased. So this is the initial volume and now this is the volume. After the addition of inert gases, volume is increased. So the molar concentration or the partial pressure of the reactants and products decreases as the volume of the mixture increases. So first, initially, this is the space. And in this space, in this small space, let me say I have 100 reactant molecules and 100 product molecules. Okay. Now this is the space. Space has got increased. Volume is increased. And also I have the some of the inert gases inside this. So what will happen to the concentration? Concentration of the reactants and products will decrease for the given space. Okay, so density is decreased. I can tell it in that way also. So in this case, what will happen? Equilibrium will get disturbed. Equilibrium will shift as in the case of increase in volume. Equilibrium will shift towards forward direction. I mean where the volume is more. To that direction, the equilibrium will shift. Got it? So this is all about the addition of inert gas. Now you see, if the number of moles of product is greater than the reactant, and if I increase the volume, equilibrium will shift towards the forward direction. So this is A and this is B. Or I'll take like this, okay? This is the reactant and it is in equilibrium with the product. If the number of moles of product is greater, if the product is 3 and if the number of moles of reactant is 2. So in this case, the number of moles of product is greater, right? So in this case, if I increase the volume, what will happen? The reaction will move towards forward direction. Okay, reaction will move towards forward direction. And for the other case, if the reactant number of mole is greater, then it will move towards backward direction. If both are equal, there is no shift. Okay. So this is the fourth factor. The addition of inert gas. Addition of inert gas. And finally, we have one more factor that affects the equilibrium, which is the addition of catalyst. Shall I go ahead with that? Have you all completed till this? The addition of inert gas has no effect for constant volume condition, but for constant pressure, it has some effect. And these are the effects which takes place by changing the volume. Okay, by addition of inert gas. The next is about the addition of catalyst. Can anyone give me the definition for catalyst? What is a catalyst? Let me see. What is catalyst, students? What is a catalyst? Okay. Catalyst means the one which alters the rate of the reaction. The one which alters the rate of the reaction or the one which is used to speed up the reaction is called as catalyst. Okay. Suppose I am having this reaction. SO2 reacts with O2 giving SO3. Kc is given. Let me draw the graph for energy versus reaction coordinate. Reactant is there and it is getting converted to a product, and this is the activation energy for the reactant molecules. At this point, the molecule is getting reacted, and this is the energy. Okay, for forward reaction. And this is the activation energy for the backward reaction. This is the activation energy for the backward reaction. If the product has to get converted to the reactant, it has to take this much of energy to get activated, to get converted to the reactant. I mean to the left side substances. Okay. Now, there is one more curve, yellow color curve. What is this curve denotes? It also denotes the activation energy only. But this is the activation energy of the forward direction reaction if the catalyst is used. Okay. And this is for the backward reaction if the catalyst is used. So what do you understand from this? If the catalyst is added to the reaction, then it is affecting the forward reaction and backward reaction in the same manner. Okay, it is affecting the forward reaction, backward reaction in the same manner. Equilibrium will not change, but the time required for the completion of reaction is reduced. Okay, equilibrium remains undisturbed, but the time required to achieve the equilibrium is getting reduced. Got it? So initially, we require this much amount of energy. Let me say that it takes around 1 hour to get activated. But if I use the catalyst, only this much amount of energy is enough to activate the reactant. Let me say this as 25 minutes. 25 minutes is enough to activate the reactant in the presence of catalyst. Equilibrium is not getting changed. Time is getting reduced. Okay. Catalyst will affect both the direction in the same manner. Got it? So addition of catalyst will not disturb the equilibrium. There is no effect on adding the catalyst. Got it? So these are the factors which affects the equilibrium condition. Shall we go ahead with some previous questions from the equilibrium? So with this, the chemical equilibrium part of the lesson is getting over. Okay. So from the next class onwards, I will talk about the ionic equilibrium. Ionic equilibrium is also the part of equilibrium lesson only. Okay. So the chemical equilibrium is getting over here. We will try to solve some questions, previous year questions from chemical equilibrium concept in today's class. And from the next class onwards, we will go ahead with the ionic equilibrium part of this lesson. Got it? So here is the first question on your screen. So all of you are going to try and give me the answer. Okay. So what is the question is saying? Kp for the following reaction is given as 3 at 1000 Kelvin. So what is given to us? Kp is given. Temperature is given. The reaction is also given. What will be the value of Kc? And R value is also given. So how to find out Kc from Kp? Which formula we have to use? We have to use the Kp-Kc relationship. Okay. So Kp is equal to Kc into RT power delta N. Right? So we have the value of Kp, which is 3. We are asked to find out Kc, and the R value is given as 0.083. Temperature is given as 1000 Kelvin. Power delta Ng. So how to find out delta Ng from the reaction? Delta Ng is equal to number of moles of gaseous product minus number of moles of gaseous reactant. So how many gaseous product we have? We have 2 moles of gaseous product we have. So it is 2 minus, we have 2 reactants, but only one is the gas, is in the gaseous form. And its number of mole is 1. The other one is in the solid form. So we should not take that. Okay. So NgR is 1. 2 minus 1 is 1. So delta Ng value is equal to 1. So you substitute 1 here. So the Kc will be 3 divided by 0.083 into 10 to the power 3 or 1000. Okay. Can anyone solve this and let me know the answer? What is the answer for this question? All of you please try solving this and find out the correct answer. Three divided by 83, right? Find out the answer. Option C. Very good. So you will get Kc is equal to 0.036. Okay. And if I keep the decimal after 3, it will be 3.6 into 10 to the power minus 2. Since I am moving the decimal towards right side, I have to keep the power of 10 in minus. Okay, if I'm moving towards left side, it will be in plus. Yeah, very good, Rakshita. Very good. So option C is the correct answer. Option C is the correct answer for this question. Very good. Shall we go for the next question? Do any of you have any doubts from this? Do any of you have doubts from this question? Shall we solve the second question? Are you all ready? Okay. So here is the second question for you. So 3O2 is in equilibrium with 2O3. Okay, oxygen is getting converted to ozone. For this above reaction at 298 Kelvin, Kc is found to be 3 into 10 to the power minus 59. If the concentration of oxygen at equilibrium is 0.040, then concentration of O3 in molar is. So concentration of one of the substances given, concentration of the second substance is asked, and the Kc value is given and the temperature is given. So how will you find out? How will you find out? First of all, you have to write the Kc for this reaction. This Kc is equal to concentration of the product raised to the stoichiometric coefficient divided by concentration of the reactant raised to the stoichiometric coefficient. Okay. So we are asked to find out the concentration of O3, right? So keep this O3 concentration one side. If I keep the O3 concentration one side, I have to take this O2 concentration to the other side, right? So it will be Kc to O2 power 3. Now substitute the values. So, this will be equal to Kc, which is 3 into 10 to the power minus 59. And the O2 concentration is given as 0.040 into 0.040 power 3. Okay. And this is O3 power 2. So O3 square is equal to. So if I multiply this, I will get 19 into 10 to the power minus 64. Okay, minus 64. So 19 means the nearest root will be, if I take the concentration of O3, I have to take the square root, right? So 16 is the nearest number to 19. Root 16 is nothing but 4. If I take this from the root, it will be 4.38 I will get. And if I take the root of this 10 power minus 64, it will, I have to divide this by 2, right? So it will be 10 to the power minus 32. If I take this from the root, it will be 10 to the power minus 32. So option A will be the correct answer. Option A, it will be around 4. 19 means it will be around 4. Okay. So 64 means if you take the root, it will get cancelled with the 2 table. So 64 by 2 you have to do, that will be 32. Got it? Shall we go for the next question? Shall we go for the next question? Okay. Here is the question. The equilibrium constant of the following are given. 3 reactions are there and the equilibrium constant is given as K1, K2, K3. Then what is the equilibrium constant for the given reaction? So from the first 3 reaction, we have to find out the equilibrium constant for the given desired reaction. So it's very easy, right? We have discussed the properties of equilibrium constant. No, from that you can find out. So here you see, I have NH3 and O2 in the left hand side and NO and H2O in the right hand side. But NH3 is given in the product side in the given reaction. So what I have to do? I have to reverse this reaction. If I reverse this reaction, I will get 2NH3 giving N2 plus 3H2. If I reverse this, I will get the NH3 in the reactant side. Okay. In which the desired reaction is having that in this left side. So since I have reversed this equation, if I am reversing, what I have to do? I have to take the reciprocal, right? So it will be 1 by K1. Okay. And coming to the next. For oxygen is given in the left hand side in the desired reaction. And here also oxygens are here in the left hand side only. So you don't have to do anything. The second reaction remains same. Where N2 plus O2 is in equilibrium with 2NO. So it remains same. Coming to the third reaction, and NO is also there in the right side. Here also it is there in the right side. So we don't have to disturb the second reaction. If you go for the third reaction, we have 3 moles of water here in the desired reaction, but we have only 1 mole of water here. So what I have to do? I have to multiply this third reaction by 3. If I multiply this reaction by 3, I will get 3H2 plus 3 by 2 O2 giving 3H2. Since I have multiplied this reaction by 3, so the number which I have multiplied has to go to the power, right? So it will be K3 power 3. Okay. So now you add all these reactions and get the new equilibrium constant. The new equilibrium constant K is equal to 1 by K1 into K2 into K3 power 3. Okay. Which is K2, K3 cube divided by K1. So in which option it is given? It is given in option A, right? So this is how you have to apply the concept from the properties of equilibrium constant. Some new reactions will be given and some of the reactions, series of reactions will be given to you. So from that, you have to take out the reaction which is, okay. If you add all these 3 reactions, the common terms will get cancelled with each other. So which is common? N2 is common, right? So cancel that. And what else is common? 3H2. 3H2, 3H2 will get cancelled with each other. And nothing else is common. So we have 2NH3 in the right hand side. 3 by 2 and 1 O2, which is actually equal to 5 by 2 O2. It is in the left hand side. Okay. It is in the left hand side. And the product we have 2NO and 3H2. 2NO and 3H2. So if I add all the reactions, I have to take the multiplication of the equilibrium constant. So that's what I have done. It is also one of the property, right? If I'm adding 2 reactions or 3 reactions, then I have to take the multiplication of the equilibrium constant of those reactions. Got it? So do you have any notes from here? Is it clear? Is this question clear to all of you? Okay, so I will ask and let you know, okay? I will ask and let you know, Episaka, okay? Don't worry. Okay, students, so time is over for us. So I am stopping the class here, okay? So I hope the chemical equilibrium part is clear to all of you. So from the next class onwards, we will go ahead with the ionic equilibrium, okay? So before going out from the class, give your feedback in the poll which I have launched, and then you can go the class, okay? So thank you so much for attending the today's lecture. So meet you all with the ionic equilibrium in the next session. Okay, till then take care. Bye bye.